RF and microwave frequencies, a real-life surface mount capacitor, or MLCC, behaves differently than an ideal capacitor. This is because real-life components include internal parasitic elements. These parasitic elements cause MLCCs to exhibit resonances at certain frequencies. These resonances are also influenced by external aspects such as the substrate and the dimensions of the solder pads on the PCB. Now, having said all this, it's clear that to accurately simulate the behavior of a real-life capacitor, you need an appropriate model for that capacitor. In terms of models, one solution comes from Modelithics. Modelithics offers microwave global models for capacitors, inductors, and resistors from many manufacturers. A microwave global model is a unique model that scales with respect to part values, substrates, and solder pad dimensions. These models make it possible to see how capacitor resonances depend on factors like K sizes, substrates, and solder pads. To demonstrate, let's look at this simple project in Keysight ADS. Here we have an ideal 1.5 picofarad capacitor model. We also have a simplified model of a real-world 1.5 picofarad capacitor. This simplified real-world capacitor has a nominal capacitance of 1.5 picofarads, along with an ESR of 580 milliohms and an ESL of 0.19 nanohenries. This simplified model is a frequently used representation. However, the reason why we're calling it a simplified model is because a real-world MLCC has additional parallel parasitic elements that are not included here. We'll get into that a little bit later on. Now finally, this project also includes the Modelithics microwave global model for the Yageo CQ0100 capacitor series. The value is set to 1.5 picofarads. Also, the substrate we'll use is 4 mm thick Rogers 4350B, and also we'll use the default values for the solder pad dimensions. Now let's go back to the simplified model of a real-world 1.5 picofarad capacitor. The simplified real-world capacitor is a series RLC circuit. We can calculate the self-resonant frequency from this equation. So we see that the self-resonant frequency decreases as the capacitance increases. At the self-resonant frequency, the total impedance reaches a minimum value that is simply equal to the ESR. Okay, now that we've said all that, let's go ahead and simulate the impedance of all three capacitors. The magenta trace here represents the impedance of the simplified real-world capacitor model, while the black trace represents the impedance of the ideal 1.5 picofarad capacitor. In the case of the ideal capacitor, the impedance only decreases as the frequency increases. The real capacitor follows the impedance curve of the ideal capacitor and then deviates. Specifically, the impedance decreases more sharply as it approaches the self-resonant frequency. At the self-resonant frequency, the impedance reaches a minimum value. Above the self-resonant frequency, the impedance increases as the frequency increases. Let's now simulate the Modelithics model for the Yageo 1.5 picofarad CQ0100 capacitor. The red trace here shows the simulated impedance. Again, for comparison, the black trace represents the impedance of the ideal 1.5 picofarad capacitor. Now, we see that the impedance of the 1.5 picofarad CQ0100 capacitor resembles the impedance of the simplified real-world capacitor model. However, above the self-resonant frequency, we do notice some differences. Specifically, we see these impedance spikes at several frequencies above the self-resonant frequency. To understand better, let's perform an S-parameter simulation of the same model in a two-port series configuration. This is the simulation schematic. Here's the simulated S21 of the 1.5 picofarad CQ0100 capacitor. For comparison, the black trace represents S21 after performing the same S-parameter simulation of the ideal 1.5 picofarad capacitor. Now, when we look at the simulated S21 of the Yageo capacitor, we see distinct attenuation notches at the same frequencies where the impedance spiked. These attenuation notches represent the parallel resonant frequencies that appear due to the parallel parasitic elements. In this case, we see the first order parallel resonant frequency at 24.05 GHz, the second order parallel resonant frequency at 36.87 GHz, the third order parallel resonant frequency at 49.23 GHz, and the fourth order parallel resonant frequency at 61.25 GHz. So the simplified real-world capacitor model may be effective to some degree, but it is not a complete representation because it omits the parallel parasitic elements. From a designer's perspective, it's critical to know if any parallel resonant frequencies fall within the intended operating frequency range. Modelithics microwave global models make it possible to identify parallel resonant frequencies to millimeter wave frequencies. Now, there are several factors that impact capacitor resonances. One factor is the capacitor's case size. To demonstrate this, let's simulate the impedance of 3 different capacitors. Here, we have 3 different microwave global models. Each one has a value of 33 picofarads. At the top, we have the microwave global model for the Chemet CBR02 series, which is an 0201 size capacitor series. This one has the smallest size out of the 3 capacitors here. Underneath that, we have the microwave global model for the larger Chemet CBR04 series. The CBR04 series is an 0402 size capacitor series. And finally, at the bottom, we have the microwave global model for the Chemet CBR06 series, which is an 0603 size capacitor series. This one is the largest of the 3. Also, the substrate that we'll use for each is 10 mil thick Rogers 4350B. This is the simulated impedance of the 0201 size CBR02 capacitor. Remember, this one is the smallest of the 3. We see a self-resonant frequency of 1.568 GHz. Now, this blue trace represents the simulated impedance of the 0402 size CBR04 capacitor. This one exhibits a lower self-resonant frequency of 1.132 GHz. And finally, this green trace represents the simulated impedance of the 0603 size CBR06 capacitor. Remember, this one is the largest of the 3. This capacitor exhibits the lowest self-resonant frequency of 968.3 MHz. So the takeaway is that increasing the case size increases the ESL and thus decreases the self-resonant frequency. Now remember that at the self-resonant frequency, the impedance reaches a minimum value that's simply equal to the capacitor's ESR. Here we see that the 0201 size CBR02 capacitor exhibits the highest ESR of 98 milliohms, while the 0603 size CBR06 capacitor exhibits the lowest ESR of 62 milliohms. So another takeaway here is that increasing the case size decreases the ESR. Let's now simulate the same 3 capacitor models in a 2-port series configuration. This time, we'll set the value of each to 6.8 picofarads. The substrate used for each one is again 10 mil thick Rogers 4350B. This is the simulated S21 of the 0201 size CBR02 capacitor. We see the first parallel resonant frequency at 11.37 GHz. Here we have the simulated S21 of the 0402 size CBR04 capacitor. We see the first parallel resonant frequency at a lower frequency of 7.82 GHz. And finally, this is the simulated S21 of the 0603 size CBR06 capacitor. Now the first parallel resonant frequency is at an even lower frequency of 6.04 GHz. Again, the parallel resonant frequencies decrease as the case size increases. So this analysis highlights the suitability of the capacitors for applications like DC blocking. The 6.8 picofarad CBR06 capacitor probably wouldn't be an appropriate choice for an application if the operating passband included the capacitor's first parallel resonant frequency of 6.04 GHz. However, the 6.8 picofarad CBR02 capacitor would be a candidate for use in more broadband applications because it exhibits a first parallel resonant frequency at a much higher frequency of 11.37 GHz. Another factor that impacts capacitor resonances is the substrate the capacitor is mounted on. Let's demonstrate this by analyzing the microwave global model for the Amotech A60F capacitor series. Here's the simulation project. On the top, we see that the model is set to 27 picofarads. Also, the substrate is 10 mil thick Rogers 4350B. Now on the bottom, we have the same model. The value is also 27 picofarads. However, for this one, the substrate is 60 mil thick Rogers 4003C. This is the simulated impedance for both cases. We see a self-resonant frequency of 1.252 GHz when the substrate is 10 mil thick Rogers 4350B. When using the 60 mil thick Rogers 4003C substrate, we see a lower self-resonant frequency of 792.1 MHz. So increasing the substrate thickness results in a lower self-resonant frequency. Let's also simulate the same model in a two-port series configuration. Again, we have the same two scenarios here. For the model at the top, the substrate is 10 mil thick Rogers 4350B, and for the one at the bottom, the substrate is 60 mil thick Rogers 4003C. Both models are set to 27 picofarads. This is the simulated S21 for both cases. Notice how we see steeper attenuation notches at the parallel resonant frequencies when using the 60 mil substrate versus the 10 mil substrate. So we see that predicting substrate-dependent performance is a key benefit of Modelithics microwave global models. Now, in addition to the substrate, the self-resonant frequency is affected by the dimensions of the solder pads that a capacitor sits on. Remember that microwave global models scale with respect to the solder pad dimensions. Therefore, we can see how the self-resonant frequency changes as the pad dimensions are varied. To demonstrate, let's analyze the microwave global model for the Amotech A60L capacitor series. This is the simulation project. The model at the top has a pad length of 17 mils, while the one at the bottom has a pad length of 28 mils. Both models are set to 24 picofarads. Also, both models have both the pad width and pad gap set to 20 mils. And finally, the substrate used here is 10 mil thick Rogers 4350B. This is the simulated impedance for both cases. We see that increasing the length of the solder pads from 17 to 28 mils causes the self-resonant frequency to decrease from 1.474 to 1.281 GHz. This is what we'd expect because increasing the length of the solder pads increases the inductance and thus lowers the self-resonant frequency. Well, that wraps up this video. For more information or to request a free trial, visit www.modelithics.com or email sales@modelithics.com.